Welcome back. We're here in section 3.1, a brand new chapter, chapter 3, and we're going to talk about determinants. So in this section, we have the topic Introduction to Determinants. So every square matrix, and it has to be a square matrix, so like a 3 by 3, 4 by 4, 7 by 7, you couldn't find the determinant of, say, a 3 by 4 matrix. But every square matrix has a real number called the determinant associated with it. So when I say real number, the determinant is going to end up being you're given some square matrix, and the determinant for it will be some real number. It might be, 5, -3, 1/2. But every square matrix has this characteristic number associated with it. So the determinant, which is often abbreviated DET, takes some matrix, square matrix, so that's what I mean. This right here is talking about the set of all square matrices whose entries are real numbers. This n squared tells us we have an n by n matrix. And to each of those square matrices, it assigns it a real number. And the way that we indicate real numbers is just this. So this is an operation that takes any square matrix, and it's going to give it a real number in a very specific way. So today we're going to focus on finding the determinant of a matrix, even before talking about why we would want to. So here in this section we're finding the determinant. There's different ways to do it, and we'll talk about them. But I do want to give you a slight preview about why this number would be useful to know. So why do we care about this, this number, the determinant? Let me give you one really brief example. And this comes from 3 Blue, 1 Brown, the Grant Sanderson, really excellent videos on linear algebra. So say that we have the unit square in R2 here, and we're going to have some transformation that takes it to, say, a 3 by 2 rectangle. So this is definitely possible and easy to do with linear transformations. So we have some transformation that takes the unit square to this guy right here, which is the 3 by 2 rectangle. And this transformation in R2 is actually represented by this matrix. We know that all linear transformations should be able to be represented by matrices, and so this transformation is represented by this one. What the determinant does, one thing the determinant does is it tells you how the volume changes from your original unit square to what the transformation takes the unit square to. This has volume 1 here, and this has volume 6 here. And so it is the case that the determinant of this transformation, this matrix, is 6. So holding on to this example in your brain, let me give you just a few quick reasons why we will care about the determinant. One way that it's helpful is the determinant can help find the inverse of a matrix in a general way, an arbitrary matrix, so for more theoretical work. Another way the determinant is helpful that we'll find is it indicates whether a system of equations, of linear equations, will have 0, 1, or many solutions. Another interpretation of the determinant is it's actually the volume of the parallelepiped formed by the columns of a matrix. And these are, this word is a weird word, but it's a geometrical object that's formed by the columns of your matrix, like we have 3, 0 and 0, 2. And so this is, in this case, this is a rectangle. It's also a parallelepiped. Parallelepiped is used because in higher dimensions, 7, 8, we talk more generally about these geometrical objects whose faces are all parallels, or parallelograms, but formed by the columns of a matrix. Okay, so that's kind of abstract there. I guess the idea I want to really convey is that the determinant, which we're going to spend a lot of time in this section just finding and knowing how to find it, has different applications. We're even going to see some soon related to eigenvalues, eigenvectors, and there's some applications in multivariable calculus that rely on the determinant. So this is a number that seemingly we pull out of thin air with this really complicated formula, but it does have a number of important uses. So now let's take some time to figure out how to find this number, this real number that's associated with every square matrix. And we'll start with 2 by 2 matrices. So finding the determinant of a 2 by 2 matrix is fairly straightforward. So A is a 2 by 2 matrix. Then the determinant of A, which is written, you can either write it as det of A, or you can write it like this, these straight vertical lines around what we know as a matrix. This will always indicate the determinant of A. So this determinant, we have A11, A12, A21, A22, and when I see these just straight vertical lines, I know that I'm not talking about the matrix anymore. At this point, I'm talking about the determinant. So this represents a real number when I have these straight lines. It's not the matrix anymore. And this equals, we're going to take these diagonal elements and multiply them, and then subtract from that this product of these diagonal elements. So the determinant of a 2 by 2 matrix is A11 times A22 minus A12 times A21. Okay, so let's run through a quick example of finding a determinant of a 2 by 2 matrix. So say that we want to find the determinant of the matrix 2, 3, 7, 4. Then that's just going to be, let's see, 2 times 4 minus 3 times 7, which is 8 minus 21, which is negative 13. And that's it. This is the determinant of the matrix 2, 3, 7, 4. So one thing this example tells us is that the determinant can be a negative number. So in your own head, go ahead and find the determinant of the matrix 3, 2, 9, 6. And I'll do it too. Okay, here the determinant equaled 0, and so definitely the determinant of a matrix could equal 0, and those will be some special cases that we want to take note of. So, because we can be working in any size square matrix, like a 7 by 7 matrix, for example, we want to be able to know how to find the determinant of not just a 2 by 2 matrix, but larger matrices also. And we're going to first define a few things. So let A be a square matrix, and we're going to define something called the minor of Aij. Before I even tell you what this definition is, let's look at an example here. Here we have a 3 by 3 matrix A square, and if we were talking about the minor of A31, well, first of all, what element is A31? Let's see, that's 1, 2, 3, 1. So here's A31 right here. And if I told you that the minor of A31 actually equals 1, and then I told you, why don't you, when you're looking for the minor of A31, we're actually going to ignore the column that A31 is in and the row that A31 is in. Just knowing that I'm eliminating that column and that row, can you tell where this number comes from? So what gets left behind is this matrix here, or this submatrix here. And what would the determinant of that be? It'd be negative 2 plus 3 is 1. So the minor of an element is when you cross out the row and column that that element is in, what's the determinant of the matrix that's left behind? So the minor of Aij, which is written with a capital M, and we say Mij, and this is the minor. We're still talking about the matrix A. This isn't a new matrix. This is all related to the matrix A. So the minor of Aij, which is written Mij, is the determinant of the matrix that remains by deleting row I and column J. Then a number that's closely related to the minor is the cofactor of that element Aij, which is written as capital C, Ij is this. Cij is Okay, so lots of letters, lots of stuff going on here, but really it's actually not as much stuff as you think it is. You just take the minor, which we found in this example, and then it's either going to be plus or minus the minor, depending on where in the matrix that element sits. So let's go back to this example over here and find the cofactor. So the cofactor of A31, which is the same thing as C31, should equal -1 to what power? I plus j. So 3 plus 1 times the minor of 31. Okay, so this equals, let's see, -1 to the 4th power is just 1, times the minor of 31. We found out that that was 1. So this whole thing equals 1. The cofactor is just 1. So in a minute we're going to pull all these together and see how it relates to the actual determinant of a matrix, but know how to find the minor, and then the cofactor is closely associated with that. It's either plus or minus the minor of an element. So the cofactor and the minor, if they're oftentimes they're the same number, but if they differ, it's only by a plus or minus sign. The cofactor is just slightly different than what the minor is. Okay, so we know what a minor is, we know what a cofactor is. Let's run through one quick example before we actually give how these even play into what the determinant is. The determinant is going to be some formula that is comprised of a lot of cofactors and some elements from the matrix. Okay, we're going to take a look at the 3 by 3 matrix, 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're going to find the minor and the cofactor of, let's just start with, actually let's do the minor and cofactor of 2, 3, element 2, 3. So the minor of 2, 3, let's see, that's second row, third column, so it's this guy right here, and we want to find the minor for this. So that the definition tells us to basically ignore the column it's in and the row it's in and find the determinant of what's left behind. So the minor of 2, 3 will be the determinant of 1, 2, 7, 8, because that's what got left behind. The matrix that got left behind, that's 8 minus 14, and that's -6. Okay, so this is the minor of 2, 3. The cofactor of the element A23 is -1 to the 2 plus 3 times the minor of 2, 3. And so this is -1 to the 5th times -6, and that's -1 times -6, and that equals 6. So the minor was -6 and the cofactor is 6, and that holds true to what we know has to be right, that they need to only be different by maybe a plus or minus sign. Another way to think of cofactors is you can think of a matrix with plus and minus signs. In the 1, 1 element, the cofactor, that first part of the cofactor will be +1, negative, positive, and so on. So this is a shorthand way of just knowing what this guy right here is. You know, we were in the 2, 3 element, so, and -1 raised to, that's an odd number, so it'll be this negative here. So you can think of, you can either evaluate this -1 to this power, or you can remember this matrix to think about what the first part of the cofactor is. So this is -1 to the I plus j. This is just a matrix that shows what it should be for each element. Okay, we're going to hold on to this formula for cofactors, and we're going to use it to give a definition of the determinant of a square matrix. So the determinant of a square matrix is the sum of, so we're going to add up a bunch of things, the sum of the products of the elements of any row or any column and their cofactors. Okay, the sum of the products of the elements of any row or column and their cofactors. So lots going on there, but we know what a cofactor is. We know what elements of a row are. So you're going to have a matrix, and you could pick any row. We could take the first row, and each element, we're going to multiply it by its cofactor, and then add it to the next element, which gets multiplied by its cofactor, and add it to the product of this element and its cofactor all the way down the line. And you could do it for this row, you could do it for this column. It'll be the same number, whichever one you choose. But this is one way to find the determinant of a square matrix. Before we go any further, let's run through an example. Let's find the determinant of this matrix. And we know that this will equal, well, looking at this matrix, we could do this work through any column, or any row or any column, and no row or column looks particularly easier or harder than the rest, so let's just run it through the first row here. So the sum of the products of the elements and their cofactors. So we'll take this element times its cofactor, this element times its cofactor, this element times its cofactor, and add all of those up together. So essentially we're taking A11 times the cofactor 11, plus A12 times its cofactor, plus A13 times its cofactor. And this will be, A11 is just 1. Now the cofactor of 1, 1, of that first element is -1 to the 1 plus 1. And then we have to think about what the minor of A11 is. Here's A11, we knock out its column and its row, and we're going to find the determinant for the remaining matrix. So we really need to find the determinant of this, what gets left behind. Okay, we'll deal with that in a second. Let's go ahead and find this part of the determinant. So this will be A12, which is 2, times -1 to the 1 plus 2. And then similarly, we're going to knock out this row and this column, and then we need to find the determinant of whatever gets left behind, so 4, 5, -2, 1. And the last guy is the 1, 3 element, so that's 4 times -1 to the 1 plus 3 times the minor of that element. So here's the element, we knock out its row and its column, and we're going to find the determinant of what's left behind. And that will be 4, -1, -2, 2. Okay, at this point, it's just a bunch of calculations. So this is, let's see, what we've got here is 1 times 1, so that's just 1. And the determinant of this, that will be -1 minus 10. So that should be -11. And then we go to 2 times, this will be 2 times -1, so that's a -2. And then the determinant of this is 4 minus a -10, so that's 4 plus 10, so that's 14. And then last guy, let's see, 4 times -1 to the 4th is 1, so just 4 here. And the determinant of that will be 8 minus 2, because -2 times -1 is 2, so 8 minus 2 is 6. Good, we're getting closer. So -11 minus 28 plus 24. Let's see, that'd be -39 plus 24. Sounds like a -15. This is it. This is the determinant of that original matrix. So definitely our calculators can do a lot of this for us, but in this section I want you to do these determinants by hand, and that's what I'm going to be grading, is seeing if you know how to calculate the determinant by hand. Okay, so here we have, I just put in my TI calculator the matrix that we just did, 4, -1, 5, just double checking. Okay, and then when we go to the matrix menu, one of the very first thing in the math menu is determinant. So you can find the determinant of A, and, oops, it didn't work. Okay, find the determinant of A. Here we go. And when I hit enter, I get -15, which is just what we calculated a minute ago. So all this work is easily checked by a calculator. I found out that the determinant really was -15, but on your homework for section 3.1, I'm looking for this work. I'm looking to see how you're doing the cofactor expansion. So please don't just put the answer, because then I can't give you nearly as much credit as I can for looking at your cofactor expansion. So in this example, we've got a 4 by 4 matrix, which that gets really ugly really fast just because there's so many cofactors, and each time you have to find a determinant, it's not just a 2x2 matrix, it's a 3x3 matrix. So we want to think of any clever ways we can minimize our work. And I notice, first of all, you think which row or which column should I expand across? And this guy right here looks like a really good column to expand across because there's so many zeros as elements that a lot of these parts of the sum will just go away. So I'm going to take this guy right here and I'm going to expand through this column. So if I find the determinant by expanding along this column, this is what the work that I should be looking to do. So I need to take this element times its cofactor, this element times its cofactor, this element times its cofactor, and this element times its cofactor. The nice thing is, because so many of these are zeros, the A13 is a 0, that'll go away. The A23 is a 0, so that'll go away. And A43 is a 0, so that goes away. So really, I just have to work on this guy right here. So let's see, the A33 element is 3, and then I need to find the determinant of what gets left behind. So I'm going to knock out this column and this row, and then I need to find the determinant of the 3x3 matrix that gets left behind. And so when I knock out this column and this row, looks like I've got 2, 1, 4, 0, negative 1, 2, 0, 1, negative 3. Okay, now I have to go through and find the determinant of this guy. And looking, there's a little bit of work involved in that too, but looking, I definitely want to expand along this column because again, I've got some 0 elements that'll just disappear. So as I'm trying to find this determinant now, and I'm going to work down this column because these zeros are so awesome. They're going to make a lot of things disappear. And so, but I do have to look at that element in the first row, first column. That's 2 times the cofactor. And so that will be negative 1 to the 1 plus 1 times the determinant of this guy, negative 1 to 1, negative 3. And that's not too bad at all. So this will be, let's see, negative 1 to the squares, that's 1, so this will be 6. And then the determinant of this guy right here, this is 3 minus 2 is just 1. So the determinant of that whole original 4x4 matrix is just 6. And I can double check this in my calculator if I want. But again, for this week's this homework on 3.1, I really want to see all this cofactor expansion and justifying why the determinant is this guy right here. But there are so many calculations along the way, and some of them get even hairier than this one, that you definitely probably want to check your solution against what the calculator finds just to make sure you don't have any arithmetic errors. One thing we want to do as we calculate these determinants is we want to minimize the work that we have to do by looking for rows and columns with lots of zeros. This was an awesome column to do, and then it led to even more fantastic zeros later on. So that really knocks a lot of your work out if you can find rows or columns with zeros to expand across as you're doing your cofactor expansion. To close out this section, we are going to look at one shortcut for finding the determinant of 3x3 matrices. We already know that 2x2 matrices are really quick. Cofactor expansion can take a long time. So there is this one shortcut for 3x3 matrices that I want to go over. So find the determinant of this matrix. This is just a generic 3x3 matrix, and we're going to find it expanding along the first row. So if I'm expanding along the first row, this will look like A11 times the cofactor of A11, which this is going to be a plus, a minus, a plus when I'm talking about cofactors. So it's the minor of A11, which will be the determinant of this. So that's A22, A23, A32, A33. And then we're going to take a subtraction because now it's a subtraction with the cofactor of A12 and the determinant of what gets left behind when we knock out that row and that column, and that's going to be determinant of A21, A23, A31, A33, and lastly we'll take a look at this guy. We'll add that'll be a positive, and then A13, the determinant of A21, A22, A31, A32, And that just comes from, we're taking the cofactors, so we knock out that row and this column, and we're left with these guys. Okay, so finding these determinants is relatively easy. So the first part of this will be A11 times this product minus this product. So this minus this. And then really similar for the next two terms. So as we look at this guy, it's minus A12, and then the determinant of that 2 by 2 matrix inside. And then as we look at this, this guy right here, it's plus A13, and the determinant of that 2 by 2 matrix. Okay, so we've got all these guys. We're going to get rid of these parentheses and rearrange a few things and then notice something cool. So at this point, let's expand. So all the parentheses are gone. And then we're going to collect all the positive terms and then all the negative terms after that. And we'll have 6 terms. Okay, so when I multiply this guy through, I get A11, A22, A33, and then I'll take it and multiply it by this guy, and this is the term I get. And then I'll go ahead and do the same thing for the rest of these terms. So here I just took the A12 and multiplied it through both of those terms. And then I took the A13 and distributed it through and got these terms. So I really do have 6 terms at this point, a bunch of A's and some little tiny numbers. And then I'm going to collect all the positive terms. So it looks like I've got one positive here, here, and here. Those are going to go first, and then behind them I'll tack on these negative terms. So that's all I've done. I've rearranged some terms. Here's the 3 positive ones, and here's the 3 negative ones. But it's all the same as the row before. It's just things are rearranged a little bit. And so this is the determinant of A. Okay. So far it still looks kind of like gibberish, like how is that even helpful? How is that even a shortcut? But now what we're going to do is go back to this and look at some patterns. And so here I've got the original matrix, and what I'm going to do, I've got these columns, I'm going to take these 2 columns and actually tack them on right here. It seems really odd, but I'm going to do it so that we can see a certain pattern. Okay, I've got the first 2 columns, these guys tacked on at the end. Now I'm going back to here. This is definitely the determinant of my 3 by 3 random 3 by 3 matrix. And look at this right here, A11, A22, A33. Okay, that's these guys here. And I'm going to go ahead and mark that, A11, A22, A33. And then I've got A12, A23, A31. So those happen to be in that diagonal. And then I've got right here A31, A21, A33. So that's that diagonal right there. Those are all my positive terms right there. Okay. I've got this first negative term, which is A11, A23, A32. So I'm going to mark that. And then I've got minus A12, A21, A33. And I'll mark that. And then lastly, I've got this last term, minus A13, A22, A31. Okay, so it looks like if I arrange my matrix like this, that I can essentially just add up these diagonals, the products of those numbers, and subtract the products of these diagonals of numbers. And that's the determinant of any random 3 by 3 matrix. So this is a shortcut. If you have a 3 by 3 matrix you're trying to find the determinant of, all I did is I tacked on the first 2 columns again, and then these very specific diagonals, I had the product of those, each of those diagonals added together, and then I subtract the product of this diagonal, subtract the product of that diagonal, and the product of this diagonal. So whichever way you want to do it, you can do cofactor expansion, but there's also this shortcut here. So let's talk about our big ideas from this section, this first section of chapter 3, where we introduce the idea of a determinant. And I told you that determinants will be useful in different ways. We haven't really seen yet how they're useful. We spent so much time just finding them in this section, but we are going to see how they're helpful. But the determinant is this idea that for any square matrix, there's this certain number associated with it that will tell you a lot of information. Okay, determinants are relatively easy to find with 2 by 2 matrices. And then for larger matrices, we introduce the idea of minors and cofactors and this whole process of finding the determinant. As you expand along a row or a column, you get to choose, and you definitely want to choose a row or column that minimizes the work to you. And then there is this little 3 by 3 shortcut for finding the determinant also.